Welcome back to the Deep Dive. Today we're taking on a topic that sounds incredibly technical, maybe even a little hackerish.
Yeah, secure shell, SSH keys.
Exactly. But if you're working with code, especially with Git, this isn't some optional, scary thing. It's really just standard procedure now.
That's the perfect way to frame it. And for you, the learner, our mission today is to, cut through the noise and give you that solid foundation. Because the bottom line is simple.
What's that?
You can't authenticate, you can't push code. It's that fundamental.
Okay, that sets the stage really clearly. But it brings up the first big question I always have. We already use usernames and passwords for, well, for everything. HTTPS, right? When we access GitLab or GitHub. So why do we need this whole other seemingly more complex system? What's the real pain point we're solving?
It's all about friction and non-interactive authentication. When you use HTTPS for a Git push or a Git pull, you're constantly having to prove who you are.
You mean typing your password over and over again?
Or relying on some caching that always seems to break at the worst possible time. It interrupts your flow. It's clunky.
So it's not just about the typing. It's that the system isn't built for that constant back and forth that you do when you're coding.
Precisely. Every little interaction is a new challenge. And that's where SSH just completely changes the game. It's the digital handshake we're talking about.
A digital handshake. I like that.
You set it up once, and from then on, your computer and GitLab, they just recognize each other. The commands just flow, no interruptions.
Okay, let's unpack that handshake then.
Yeah.
This gets us right to the core concept, right? The whole public versus private key thing.
Yes. And if you only take one thing away from this, this should be it. This idea of an asymmetric key pair. We always use the lock and key analogy because, honestly, it just works.
It's foolproof. So, following that analogy, let's start with the lock. What's the lock?
The public key is the lock. And the most important thing to know about the lock is that you can give it to anyone. You can share it freely. You take that public key and you literally upload it to your GitLab account. You're telling the server, hey, put this specific lock on the door to my account.
So you're basically saying only someone with the right key for this lock can get in.
Exactly. And that key, the private key, is the one you have to protect.
It's the physical key in your pocket.
Yes. It never, ever leaves your computer. It has to be guarded. When you try to connect, your machine uses that private key to sign the request, and the server uses the public key, the lock, to check the signature. If they match, you're in, instantly. No password needed.
Okay, I see a classic beginner mistake coming, a huge security hole. What happens if I get them mixed up? If I accidentally upload my private key to GitLab?
So first, that would be a massive security failure. But thankfully, the system is designed to stop you.
Oh, it don't even let you.
It'll just reject it. The formats are different. The server's expecting a public key. And what you're giving it just doesn't look right. So it fails safely. But it all comes back to that simple rule.
Public is for the server. Private is secret.
That's the memory hook. If you remember that, you can't go wrong.
Love it. Okay, that makes perfect sense. So let's get practical. How do we actually generate these two files on our computer? What's the command?
It's a single command you run in your terminal. ssh-keygen.
Just that.
Just that. It does all the cryptographic heavy lifting for you and creates the pair of keys usually in a hidden .sh directory in your home folder.
Now, I know there are different types. People used to always use iDressa, but I've been seeing sources recommend something newer.
That's a super important point for anyone setting this up today. iDressa still works, but the modern standard is A25519.
And how do you generate that specific type?
You just add a little flag, ssh-keygen, ssh-keygen 25519.
So why the change? Why is ed 255?
Ed 25519. Yeah, it's just better. The keys are smaller, they're faster to generate, faster to verify, and the security is just as strong, if not stronger, than the old, much longer RSA keys. It's just better practice.
Okay, so we run the command. We get two new files. Probably I did 255.9 and I did 255.longtime.pub. How do I know which one is the secret I have to guard?
It's the file extension. The one with .pub at the end is the public key. That's the one you can share.
So the file without an extension is the private one.
Correct. Guard that one with your life. The .pub file just contains a string of text you copy and paste into GitLab.
Now, when you run ssh-keygen, it also asks you for a passphrase. And I know a lot of people just hit enter and skip this. Is that a bad idea?
It's a very bad idea. That passphrase is what protects the key file itself. Think about it. If someone gets a copy of your private key file, but you've protected it with a strong passphrase, it's still useless to them. It's a critical layer of security.
Right. So we've copied the text from the .pub file. We've pasted it into our GitLab preferences. But there's one more step that trips up literally everyone. File permissions.
Ah, yes. The classic permissions are too open error.
Exactly. What is that all about?
It's your own computer protecting you from yourself. The SSH program will refuse to use a private key if the file permissions allow anyone other than you to read it.
So you have to lock it down.
You have to. You run a command, chmod 400, on the private key file that basically says only the owner you can read it, no one else. If you don't do that, the system assumes your key is compromised and won't use it.
That's a fantastic troubleshooting tip right there. The system is forcing you to be secure.
Exactly.
So before we move on, the sources mentioned another neat security feature in GitLab, key expiration. Why is that such a smart idea?
It's proactive security. Think about a large team. People come and go. Laptops get lost. If a key is set to expire in, say, 90 days, access is automatically revoked, even if someone forgets to manually remove it.
It just shrinks the window of opportunity for a lost key to be misused.
It turns key management from this reactive chore into an automated, secure process. It's a huge win.
Okay, let's add the next layer of complexity, the SSH agent. Because if I follow the best practice and use a strong passphrase on my key, now I'm back to typing something every time I do a git command. We're back to the original friction problem.
Right. You've solved one problem and created another. That is exactly what the SSH agent is for. It's a little background process that's always running on your computer.
So what does it do?
The first time you need your key after you log in, you type your passphrase once. The agent then loads the unlocked key into your computer's memory.
Oh, so it's like the password manager, but just for your SSH keys.
That's a perfect analogy. It is exactly that. For the rest of your session, anytime you need the key, the system just asks the agent and the agent handles it silently. You don't type the passphrase again until you reboot.
Okay, but I want to push back on that a little from a security perspective.
Yeah.
We just talked about guarding the private key on the disk so fiercely. And now we're taking its unlocked, most sensitive form and just sticking it in RAM. Doesn't that just move the risk?
That is an excellent, critical question, and the answer is yes, it does move the risk. But it's a calculated trade-off.
How so?
That memory is volatile. It's only there while your session is active. If someone compromises your machine while the agent is running, yes, they could potentially extract the key. But the alternative is what?
Typing the passphrase 1,000 times a day.
Or worse, people just won't use a passphrase at all to avoid the hassle, leaving the key totally unprotected on the disk forever.
So we accept a temporary session-based risk in memory in exchange for having much stronger protection for the key when it's just sitting on the hard drive.
Exactly. It's a smart compromise between security and usability.
Got it. Okay, let's pivot to where this gets really powerful. CI/CD, continuous integration pipelines. We have these runners, these automated robots executing jobs. Why on earth would a robot need an SSH key?
This is often the final piece of the puzzle for someone moving into a DevOps role. The runner is just a dumb server. It's not you. If a job needs to, say, pull code from 3 other private repositories to build your application.
Yeah, so it needs to access things outside of its own project.
Exactly. Or maybe the final step is to deploy the code to a secure server that only allows SSH connections. The runner has to prove it has permission to do that. It needs credentials.
So how do you give a temporary CI/CD job a private key without just pasting the secret into a file that anyone can see? That sounds like a terrible idea.
It is a terrible idea. The right way is to use secure variables. In GitLab, for instance, you store the private key as a CI/CD variable, and this is critical. You have to set it as a file type variable.
A file type variable. Why is that specific part so important?
Because the SSH client program needs a path to a key file. It doesn't just take a string of text. So when you use the file type, the runner writes the secret key to a temporary file for the job and then just tells your script where that file is.
So the key isn't just floating around as a normal variable that could leak into the logs. It exists as a file just for that job, and then it's gone.
Precisely. But even then, you're not done. There are 2 security settings you must enable on that variable. This is non-negotiable.
Okay, what are they?
It must be masked and protected.
Masked and protected. What does masked do?
Masking tells the system to watch the job logs. If that secret key value ever accidentally gets printed out, the system will automatically replace it with asterisks. It prevents a leak.
And protected.
That limits when the key can be used. It ensures the variable is only available to jobs running on specific secure branches, like your main or release branches, so someone can't just run a random pipeline on a feature branch and steal your deployment key.
Wow. So it shows that security isn't just about the tech, it's about the process. Forgetting to click those 2 checkboxes is a major security failure.
It's the difference between secure automation and creating a massive, gaping vulnerability.
We've covered so much ground here, from just being tired of typing a password all the way to securing an enterprise CI/CD pipeline. Let's do a quick final recap for everyone listening.
For sure. Remember, SSH is all about replacing that slow password entry with a fast, secure digital handshake.
Right. And the model is lock and key. Public key is the lock. That goes on the server on GitLab.
And the private key is the key. You make it with ssh-keygen, -DAD 25599. You protect it with a passphrase, and it never, ever leaves your machine. Lock it down with Shimon 400.
And the SSH agent is your helper, your little key manager, holding that passphrase in memory so you don't have to.
And for CI/CD, that private key becomes a file type variable that is always, always masked and protected.
So the final reinforced memory hook, the one thing to tattoo on your brain.
Public equals server, private equals secret. Get that right, and everything else falls into place.
Fantastic. So we've established the private key must be guarded, and you can set expiration dates, which is a great defense. So here's a final thought for you to chew on. Knowing that the SSH agent holds your unlocked passphrase in memory for convenience, which is a potential risk, how do you personally balance that? Do you use a super complex passphrase that forces you to rely on the agent, or a simpler one you might type more often, which would limit the time that unlocked key is just sitting in RAM?
That's the constant battle, isn't it? The tension between perfect security and practical usability. Something to think about next time you run ssh-keygen.
Exactly. Thanks for diving deep with us. We'll catch you next time.